Pretty good. How are you?
Good. All right. Let's see. We got through question 14. Skipped a couple, and if we have time today, we'll go back and look at those two. But let's look at 15. Now, the first thing you want to understand about these word problems is that you're going to end up with a triangle. In other words, 15 is going to be the same as 13 and 14. You're going to end up with a triangle where you have three pieces of information. And you need to solve for a fourth piece. So, let's look at this. You have two airplanes taking off in different directions. Let's see, how can I do this? One's going due east. Let me just start this by doing this. Hold on. There we go. Finally got it to work. Okay, so if we draw a picture, one flies due east. Which way is that? Right, left, up, or down?
Right.
At 350 miles per hour. The other flies east, northeast. Which way is that?
That's like diagonally right up.
So how many degrees is it? From the angle that we're looking at. In other words, this is north, right? So east, northeast means that.
Yeah.
So that's 45 degrees. And that's important. We need that information. And it's flying at 380 miles.
Yep.
And they want to know how far apart the planes are 2 hours after they separate. All right. Well, I need to do this a little different. Let's do it this way. This one's going 380. This one's going 350. Was that correct?
It was 350 and yeah, 380.
Okay. But they're going for 2 hours. So if I draw a triangle, what are my dimensions going to be? I know that there's a 45-degree angle between them, but how far does that plane travel in 2 hours?
760.
Well, the top
one's 400
and the bottom one is 760. Okay, so there's our triangle. What kind of triangle is that in terms of geometry? Is it side, side, side? Is it side, angle, side? Is it angle, side, side? What is it?
It's angle, side, side.
No, actually not. Angle, side, side would be if I had 700 and x. That would be angle, side, side.
Okay. So, side, angle, side?
Side, angle, side. And what do we know about side, angle, side? How do we solve this?
the laws of,
How do we start it? Can we use the law of sines?
yes.
Tell me how to do it. Tell me an equation I can write.
So you could do the sine of A, big A, over
45 degrees.
45 over little a.
What's that equal to? Notice you can't find what it's equal to. Because we're going to have two variables. It is equal to the sine of b over little b. But first of all, we don't know what angle b is. We know what little b is. But that still leaves us two variables. We cannot solve an equation that has two variables in it. So we cannot use the law of sines. In order to use the law of sines, you've got to have one angle and its opposite side. You do not see that in this picture. You got an angle, but you don't know its opposite side. You got two sides, but you don't know their opposite angles. So angle side calls for the law of cosine. Just like side does. Those two. Okay. So, how am I going to solve this using cosine?
So, you could do
I suggest starting everything with that.
okay.
In other words, a squared. Little a squared is equal to what?
B squared.
B squared plus
C squared.
Keep going.
Minus 2BC cosine A.
And the reason I said start with that little a is because we know what that is, we know what that is, we know what that is, and we're going to be able to figure out what that is. So everything on the right side of the equation is a known. So we're going to be able to solve for a. So b is 760 squared plus 700 squared minus 2 times 700 times 760 times the cosine of 45 degrees. Well, that's one big number. Figure it out on your calculator and then take the square root of it, and that will give you side A. Now, let's think back for a second. What did they want? They wanted the distance between the two planes. That is side A, isn't it?
Mm-hmm.
Okay? So that'll give us exactly what they want. We don't need to solve this triangle. Because all we need to do is solve for side A, little side A. So what do you get when you put all this into your calculator?
Um, 315,238.38.
Take the square root of it.
No.
In other words, little a is equal to the square root of everything you see above it. Because everything you see above it was equal to a squared.
Yeah.
So what's little a
So-
equal to?
561 point.
That makes a lot more sense, right? In the context of the numbers we're talking about.
Mm-hmm.
One plane goes 760 miles, the other one goes 700 miles in a different direction. You certainly would not expect them to be 56,000 miles apart. Impossible. But they could easily be that amount. And that's going to be the answer. Okay? So, this problem, you had to draw a picture. Then you had to realize that you were looking at side angle side. And then you have to know that the only way to solve a side angle side triangle is by starting with the law of cosine.
Yep.
All right. Two meteorologists are 25 miles apart on an east-west road. Let me see if I can draw this on the screen as opposed to a separate one. So here's the east-west road. Okay? Got one meteorologist there, another one there. 25 miles apart. Meteorologist at point A cites a tornado 38 degrees east of north. Well, if I put a north-south line there, 38 degrees means that angle, excuse me. No, actually, that's correct, I think. Yeah. 38 degrees east of north means you start by north and you go 38 degrees east. So that's the 38 degree angle right there. Okay?
Okay.
Some big tornado right there. In other words, is all the meteorologist notes is the angle that he sees that tornado at. He doesn't know how far away he is from it.
Right.
The meteorologist at point B cites the same tornado at 53 degrees west of north, which is like that. Now, what's really going on here, let's redraw this picture. It's the same tornado.
Uh-huh.
So let's make that tornado right there. Now, if I draw a line to the first meteorologist, that's 38 degrees east of north. And if I draw a line from the other meteorologist, that is 53 degrees west of north. Now, let's see what that means. If I draw a line right down through that, so we got to figure out some of these angles, okay?
Mm-hmm.
So if I were to extend that line, there's the 38 degree angle, which makes that 38, which makes this 52. That's a right triangle. With me? First
Yep.
of all, do you see how I got the 38-degree angle?
Yeah.
Okay. And if I extend the line from B, I know that that is 53 degrees, which makes that 53 degrees, which makes that 37 degrees. Okay? So, here's the triangle that I have. It's 25 miles. That's 52 degrees. That's 37 degrees. What is that total? That totals 89. That must be 91 degrees. In other words, whenever they give you two angles of a triangle, the very first thing you should do is just go ahead and calculate the third angle. That's the easiest thing to do.
Right.
Okay. Now, what they want is the distance from each meteorologist. So the first meteorologist is X distance from the tornado. Second one is Y distance from the tornado. And they also want the distance between the tornado and the road. So they want this line right there. So let's work with that.
Okay.
First of all, what kind of a triangle is this?
Obtuse. Yeah. Okay.
Well, it started out being angle, side, angle, right?
Oh, yes. Yes. Yeah.
Okay. Well, when you have angle, side, angle, you really have angle, 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 side, which we showed.
Mm-hmm.
So how do we solve for x? Which law do we, let's table the last part for the last part. Let's work with just this for a moment. I don't want to confuse the issue. So we need to solve for x and y.
Mm-hmm.
Which law are we going to use?
Since we have the three angles, we can do right.
You only have two. You have the law of sines, the law of cosines. You
Yeah.
always have to use one of those to solve triangles that are not right triangles. This is not a right triangle. So which
Law of cosines.
law of sines or cosines?
Cosines.
One?
Cosines.
Always use the law of sines if you can. Always. Can we use the law of sines? What do we need to use the law of sines?
At least two sides.
Just one.
Just
We
one.
need one angle and its opposite side. That's it.
Okay.
So the first part of the equation is the sine of 91 degrees divided by 25. That gives us a ratio that is the same for every angle on this triangle.
Okay.
What's on the other side of the equal sign?
Sine of little b. Oh wait, no, big B, which is 52 degrees. No.
That's what I wanted. I didn't want a letter. I wanted a degree. Over what?
Over. Wait,
What's
I
opposite
think
52 degrees?
52. Y.
It's always the angle that it's opposite the side. when you're using the law of sines, that's the most important thing. Choose the side that is opposite the angle that you're taking the sine of. Okay? Now, there's only one variable in that, and that's y. So if I cross multiply and then divide by sine of 91, you get this. Give me a number on that. That's what y is going to be.
So, negative 28.5.
Okay, it can't be negative. First of all, sine of 52 degrees in the first quadrant, that's positive. Sine of 91 degrees is in the second quadrant, that is positive. So I've got nothing but positive numbers.
No. 19.7.
Okay, so that's 19.7. That's how far the second meteorologist is from the tornado. Right there. Okay? Now let's figure out the first one. What equation solves for x? I don't need to use a different ratio than I used on the first one. This ratio right here holds for all three angles in that triangle.
So, okay. So sine of 91 over 25.
Not hearing you, Demetrius. Speak up.
Oh, sorry. Equals sine of 37.
Okay.
Over x.
Again, we have an equation, only one variable, x. So I'm going to cross multiply.
Sure. Let me show you.
Yeah.
A 3, a 5, a 3, 5, 4. I think you say, let me show you.
So what's x equal to? Having a hard time hearing you, Demetrius. I hear a lot of background noise.
Oh, yeah, sorry. I was just mumbling there because I was putting it into my calculator. The answer is 15.04.
Okay. Does that picture make sense?
Yep.
Does. Got the smallest side opposite the smallest angle, the largest side opposite the largest angle.
What?
So we have figured out how far each meteorologist is from the tornado. Now we have to figure out how far the tornado is from the road.
Yeah.
Well, let's see. How can we do that? I can think of a way. I'm just not sure it's the most efficient way. Figure out the distance on that line.
Find fairy tale heroes, except for the giant. Maybe you should write that down.
Sure, that's a right angle. They're a trig function. In other words, we're dealing with this triangle right there, right? Which is a right triangle. You don't need that much to solve a right triangle. You don't need law of sines. You don't need law of cosine. The trig function will solve for z. I will call it z.
So
What two things do we want to relate? We want to relate z to what?
to the 25.
No, because we don't know that that's 25. We don't know what this distance is. We're dealing with triangle number 1. So we don't know whether that's 20. It's not 25. It's some fraction of 25, but we don't know what it is. What do we know?
The 15.04.
Okay. So what relates Z to 15.04 and this angle that is the only angle we know? Which trig function? Which trig function relates the opposite side to the hypotenuse?
Tangent. No. Sine.
Okay, so give me the equation.
So sine equals.
Hold on. Sine never equals anything. Trig functions are always trig functions of an angle. In other words, there needs to be an argument there that is an angle.
So sine of 52
equals what?
Equals 15.04.
Nope. What's sine equal to?
Z. Z.
What's sine equal to based on SOHCAHTOA?
The hypotenuse.
What does O mean?
Opposite.
And there's always an over between these. They don't say, but you're supposed to assume. So it means opposite over hypotenuse. So what is opposite?
The Z.
What's the hypotenuse?
15.04.
Yeah. So hold on.
That lets you solve for Z. Z is equal to 15.04 times the sine of 52 degrees. Go ahead and come up with that number.
11.82.
I'm sorry, I didn't hear.
11.82.
That's how far the tornado is from the road, perpendicularly, measured perpendicularly. 11.82, and that fits with all of other measurements. If I had to come up with 118 miles, I know something's wrong. The critical part of this entire problem was drawing the diagram properly. Okay?
Okay.
And that's not all that easy to do when they give you east of north. In other words, east of north means that angle right there. 38 degrees east of north. But notice that if that's 38 degrees, this one has to be 52 degrees.
Mm-hmm.
So you have to take these 38 degrees east of north and 53 degrees west of north and put them together in a triangle, like I did.
Right.
All right. Let's go back and look at, I actually have a reluctance to do this because these are level 9 and you're having trouble doing level 5. So I'm not sure why we'd want to spend our time talking about level 9 problems. That's a level 9 problem, so is this one. Everything else on here is at best a level 5 problem. That's on a 10-point scale. Okay?
Okay. All right.
So if you had additional problems, it would be much better if we worked on those rather than these two.
Okay. Yeah.
You have
I was
additional ones?
I was gonna send you a picture.
Okay,
Yeah.
go ahead and send me a picture, another one. Because I think it's really kind of silly. It would take us 20 minutes to do this problem. And it would take us another 20 minutes to do that problem. These are way too tough. In the sense that you need to know how to do these easy ones. That's what's going to give you the best grade on your test. It's not doing the level 9 problems. It's making sure you can do all the level 4, 5, and 6 problems.
Okay.
Tell me when it says file sent on your end.
I believe it's sent. Oh wait, no, sorry, it's still sending.
Yeah, it's not going to show up on my end until it says file sent on your end. And then it takes about 15 or 20 seconds after that.
Mm-hmm. Yeah, it's not.
Using
Okay,
iPhone?
no,
Okay.
I'm on Samsung. It's just sent.
Okay, cool. Did you send it to David Cowan 1949 at gmail.com?
Yeah.
Because I do have another email address that doesn't get to me quite as quickly. It's David at digitalmathtutor.com.
Yeah, let me see.
Because I haven't gotten this one yet.
No, that's perfect. That's perfect. No, that's perfect. I'm perfect.
Yeah, I sent it to the right email. Oh wait, no, I didn't. Wait, it didn't say. For some reason, it's still sending.
Looks like previous one you sent my correct email. In other words, this is the correct email right here. David Cowan 1949 at gmail.com. That's where you want to send it.
Right. Yeah.
Are there any parts of it that you can verbalize?
Uh,
I mean, I'd
It
rather
looks like
you
it just
send it to
sent.
me, but I don't want to waste our whole session trying to solve that problem.
Yeah. It looks like it's sent.
Okay. I got it. Unfortunately, I have to do a lengthy routine to pull it up. It'll be a minute or so. All right. Okay, so that's downloaded, which means I'm not sure this is the fastest way to do this, but it works.
That's it.
That's it?
Yeah. So I've already done problems 1 through 10.
1 through 10?
Yep.
So let's talk about doing 11. When you are converting from polar to rectangular or from rectangular to polar, there are 3 equations that are really important that you memorize. Okay? First of all, this is in polar. So this is R. Hold on. Let me get this to where I can write it. This is R. This is theta. Okay?
Okay.
And the 3 equations that are vital are r squared equals x squared plus y squared. That's not the most important one. Most important one is x equals r cosine of theta and y equals r sine of theta.
Okay.
Those 3 equations will allow you to switch back and forth between polar and rectangular coordinates.
Right.
So, what we need to do is figure out what x and y are, because those are our rectangular letters.
Yep.
Okay, so let's start with x. X is r cosine of theta, which is what in this case?
So 3 cosine of pi over 6.
And y is
3 sine of pi over 6.
so this becomes, what's the x coordinate? What's that equal to? Your calculator isn't going to help here because they want a real answer. They don't want a decimal answer. What's pi over 6, first of all? What angle?
That's 30 degrees.
Okay, what's cosine of 30 degrees?
Root 3 over 2.
Good. So this is 3 times that. There's your x coordinate. Now what's your y coordinate?
So that's 1/2.
Okay, so that's 3 halves.
Yep.
And that's how you do it. It's as simple as that. And notice we didn't even need that top equation yet. You rarely need that one, to be honest with you. The 2 most important ones are those 2 that I have written there.
Right.
Okay.
Cool.
So now let's go the other way. Convert the rectangular coordinates to 2 different polar coordinates. And the rectangular coordinates are minus root 3 comma 1. So let's do this. So x is equal to minus root 3. Y is equal to 1. And we have to convert that to r and theta. some r, and some theta.
Right.
Well, r, remember r squared was equal to x squared plus y squared? So let's do that one first. That's easy.
So r squared equals -3.
No, you're squaring that whole thing. What do you get when you square that?
So 3.
Okay. So r equals r squared equals 3 plus what's y squared?
1.
So what's r equal to?
So r equals 2.
Okay. Now, we need to figure out theta, and we haven't done this yet. But theta is always equal to the inverse tangent of x over, of y over x. In other words, let's talk about that for a moment. In polar coordinates, that's theta, right?
Yeah.
That's x, that's y. So notice that the tangent of theta is equal to y over x, which makes theta equal to the inverse tangent of y over x. So let's figure out what theta is. What's the inverse tangent? We figured out, here's our x and y. So we've got 1 over negative root 3. Now, before you answer, let's back up a little bit. The easiest way to remember this is the following. And this is going to be different. Theta equals the inverse tangent of y over x if x is positive.
Okay.
If x is negative, then it's equal to the inverse tan of y over x plus pi, putting it into a different quadrant if x is negative.
Okay.
Well, in this case, x is negative. Okay, so first of all, what's the inverse tan of 1 over negative root 3?
So that's,
Use your triangles. What angle is that? Figure out where the inverse tan is 1 over square root of 3. That'll tell you the first quadrant angle. Again, back to my triangles. You can't do anything in trig unless you know these triangles.
right.
So where is the tangent equal to 1 over square root of 3? Tangent of which angle?
90.
It's never 90. It's either 30 or 60.
So,
And I meant that realistically. The answer is never 90 on these. Not when you're dealing with a number like this.
okay.
In other words, what would the tangent of 30 degrees be?
It would just be 1.
SOHCAHTOA. Got to start with SOHCAHTOA. Tangent is opposite over adjacent. What's the tangent of 30 degrees?
1 over root 3.
Ah, that's the number we're looking at. So this would normally be 30 degrees if it was positive, but this is negative. So that is a fourth quadrant angle. What is the equivalent fourth quadrant angle to 30 degrees?
11 pi over 6.
Yeah, let's call it 330 for the moment.
Okay.
Okay. But I have to add 180 to that because x is negative. And this is where it gets a little tricky. But trust me, this is the easiest way to figure it out. Okay?
Okay.
So, what does that total? That totals 510. Well, that's not inside the unit circle. How do we make 510 degrees inside the unit circle?
You subtract 360.
Yeah, which gives us 150. So theta is 150 degrees.
Okay.
Now, the reason this is strange is because usually you want to know whether that thing is positive or negative, but not in this particular case. When you're switching between polar and rectangular, it's the denominator that matters. In other words, it's only x. If x is negative, then we have to add 180 degrees to our answer. If x is not, then it's just equal to the inverse tan of y over x. Okay? So, that is one answer right there. Now, they said they wanted 2 answers. Well, in all polar coordinates, you actually have an infinite number of answers. You do. Let me show you why. First of all, let me start with a real simple example. 45 degrees and 1. Okay?
Okay.
This point right there would have polar coordinates of 1, 45 degrees. But I could also say, instead of going 45 degrees, let's go 225 degrees this way, and then let's go -1, which causes the thing to go in the opposite direction. So you end up in the same point. If you go -1, 225 degrees. That gives you the same x and y coordinate. Okay?
Yep.
All right. So let's check our... Now, the one thing about polar and rectangular is they can be plotted on the same exact plane. Okay?
Okay.
In other words, I know what my rectangular points are. It's minus square root of 3. Well, square root of 3 is about 1.7. So I'll go out to minus square root of 3. And then it's up 1. So that's the rectangular point, minus root 3, 1. Okay?
Okay.
And this point right there, the polar coordinates, needs to fall on that same point. Well, the first thing you do is do the angle. Well, that's a 150 degree angle right there. And then you go out a distance of 2. So the question is that point the same point? Well, if I make a triangle, I know that's root 3, that's 2. If you do the math, excuse me, that's not 2. What do we get for a y? Yeah, the y coordinate
is
is
1.
Excuse me, that's 1. Okay. So if we look at this triangle right there, just draw it separately. We've got this is root 3. This is 1. The hypotenuse should be 2 if we use just the Pythagorean theorem.
Yeah.
And it is. In other words, the polar coordinates 2, 150 degrees put you on exactly the same point as the rectangular coordinates do. And that's important to understand, that they're the same. They can be overlaid on one another. The rectangular and the polar coordinates can be plotted on the same graph, and they should each result in the same point.
Okay.
Now, I think I gave you an answer. Let's see. If I wanted to go this way, -2, then I would have to go 330 degrees, -2. That gives you the same point, the same exact point right there. And
Okay.
the way you do it is you always do the angle first. Okay? So notice I did 330 degrees, giving us this ray right there. But then -2 means I don't go in this direction, I go in the opposite direction. So I go that way, putting me right on my original point. So this polar coordinate and this polar coordinate are the same. The same point on the XY plane. And that's one of the difference between the rectangular coordinates and polar coordinates. Rectangular coordinates, this point right here, can only be described in one way, -√3, 1 in rectangular coordinates. But in polar coordinates, there's an infinite number of ways to describe that same point.
Okay. Yeah.
All right.
Okay. Give me 1 second. I'm going to grab another piece of paper.
Okay.
All right.
All right, we only have 5 minutes, and unfortunately, I do have another appointment that I've got to get to, but I think I got time to do one of these. And the way you do these, the way you graph polar coordinates, is you make a table.
Okay.
And the table at the top has r and theta. Okay?
Right.
So let's pick some thetas. Let's pick 60 degrees. What's r?
So is that the radian. So
Well, just plug in 60 degrees for theta and figure out what 3 plus 2 cosine of 60 degrees is. What's cosine of 60 degrees, first of all?
It's √3/2.
No. Here's a good thing to remember. The sine of 30 is the same as the cosine of 60. The sine of 20 is the same as the cosine of 70.
Okay.
In other words, the sine of x is always equal to the cosine of 90 degrees minus x. So we know that the sine of 30 degrees is 1/2. Therefore, the cosine of 60 degrees is 1/2.
Okay.
If you do the math, you get r equals 4. Now, that just gives you 1 point. In other words, I can go out 60 degrees, up 4 on that diagonal. There's 1 point on my curve. Okay?
Right.
Now we need to find some other points because this is I believe it's a cardioid, is what it's called. These different polar equations produce different types of shapes. And to get another point, let's put in another angle. Let's try 30 degrees. What's r when theta is 30 degrees?
So it's crap. This cosine.
Plug it in. Plug it into that. What's cosine of 30 degrees?
That's √3/2.
Okay. So what we have is 3 plus √3.
Mm-hmm.
And that's when we're at a 30-degree angle. So if I make my thing at a 30-degree angle and go up 3 plus √3, that's actually further than the first one. Goes to about right there. So there's another point. Okay?
Okay.
Now, oops, hold on. I could plug in various angles. Let's plug in 0. What's cosine of 0?
0.
No. Demetrius, the best thing you could do for yourself is memorize what the sine and cosine of these common angles between 0 and 90 are. Seriously. That is the best absolute thing you could do for yourself. So that they are on the tip of your tongue every single time. Cosine of 0 is 1. Which makes r 5. Okay. Well, 0 is this line right here. And I'm going to go out to 5. So this distance is 5. So now I've got this point, and this point. If I figured out a bunch of other points, I think it's going to give me something that looks like this. It's a common shape in polar coordinates called a cardioid. And all cardioids have the formula r equals some number plus another number times a cosine of theta. That is the standard equation of a cardioid. And there's a reason it's called a cardioid. Notice that looks like a heart.
Yep.
That's why it's called cardioids. It's because it's in the shape of a heart. And
Okay.
I could get every one of these points by filling out the table completely with all of the various angles that are involved in constructing that cardioid. And
Okay.
you're going to basically have to do that with all of them. Now, there are tables in your book that will tell you this is a particular type of graph. It's a cardioid, or it's a Archimedes circle, which is like this, a spiral. Some of them come out like that. So there's different shapes, but the most standard one is these cardioids or flowers. In fact, this could be a flower. The flowers tend to look like this. Three-petaled flower, only this part here is like that, okay? And right offhand, I don't know. That might be a flower. That might be a flower. That might be a flower. Some of these are cardioids. Some of them are flowers. And the numbers tell you how many petals there are in that flower. But listen, I really am going to have to run.
Okay.
But that's the basics of equation.
Okay.
Demetrius, I'll talk to you next time.
Sounds good.
All right. Bye-bye.
Bye.